Hello everyone, it's been a while. Today I want to compare the boundary conditions in CST Studio. I think in one of my videos I mentioned that I really did not have so much of an idea if the waveguide port boundary condition overrides every other boundary condition. I suspected as much that it does from my simulation, but I never really had any checks to see that it actually does this, because I think different software would have their own different implementation of their boundary conditions and which of these boundary conditions takes precedence. So I'm going to give a summary before I dive into the video. The goal was to see first, the main motivation for this was to see the absorbing properties of the different boundary conditions, especially the open boundary condition. That was the initial goal, but then I was like, okay, I could just use this opportunity to test and see what actually happens when you have a waveguide boundary condition and then you define a different boundary condition. So I'm going to go through the summary for those that are already well versed with CST Studio and just are curious to see what the results were. I'll go through that and then I'll now do a deep dive into how I went about this and show the different results. So for the simulation, I have a basic waveguide. These are the dimensions, so you could replicate it. And the only thing I changed, so I have an excitation source, which is your waveguide port here at port 1. And the only thing I changed throughout the simulations is the boundary condition at the other end. So by changing the boundary condition at Z mean, I have electric, magnetic, open at space, and conducting wall. I did not check periodic. So what were the results for the perfect electric conductor? Expected full reflection. Maybe I'll just pull up the result here if I haven't missed anything. So what I'm looking at is the S11 parameter, so the amount of energy for this should be the T11 mode. I excited just one mode first. I also have a case where I excited 3 modes. So for the T11 mode, I'm checking how much of the wave that is propagated through the waveguide is reflected back to the port. So these are the results. For the peg boundary condition, I expected full reflection. That's the mode is reflected and back. So what I'm plotting here is the S11 parameters. Yeah, I should have put S11 magnitude, but it's okay. At the S11, the magnitude of the S11 parameters in decibels. And what I have from the PEC boundary condition, you can't see it, but it's under this red line. So the PEC, the conducting wall, they both behave the same, which is at the cutoff frequency or for this particular waveguide, which is around 750 megahertz. And also this is wrong. This should be in gigahertz. Yeah, I didn't check my scale. So the frequency is in gigahertz. So for 700 and the dimensions are in millimeters. So for 750 from 750 megahertz, which is the cutoff frequency for this particular waveguide, you have that every mode which is supposed to propagate is reflected back by this boundary condition. So your PEC, your conducting wall, which I use copper, but I expect all conductors to behave exactly the same, which is you have total reflection of the wave. And then I also check for the open, for the PMC. So for the PMC, you also have the same effect. They all are under the red line, so all of the transmission curves under the red line, so you have reflection. Then what was interesting for me to see was that the open boundary condition does not give you a total absorption. Why is this file name here? Does not give you a total why is this here? Okay, it doesn't give a total absorption of the propagated waves into the cavity, and you see that this is most especially prominent at frequencies which are close to the cutoff frequency, and then you see that you have an exponential decay of the absorption or reflection in this case for the S11. So I don't know. For me, I was on the impression that the open boundary conditions you have that all the waves are propagated through. So I assumed that it was a perfect absorber, but then you see that at these frequencies you have reflections, which are not exactly zero. So you do not have a perfect transmission. You also do not have a perfect absorption of the waves. And then even up to, I mean, I studied up to 2 gigahertz, which is some distance away, some frequency distance away from your cutoff frequency, and then you still have like minus 30 dB. Then for the waveguide port, you had really good absorption of the wave, even up to high frequencies. So the conclusion of this was that the waveguide port overwrites every other boundary condition that you have. So if you should put a waveguide port at Z min, so at any port at all for any problem you're studying, and then for example you now specify here that you have a PEC, then the waveguide port overwrites it. You do not notice reflection as is seen for this example. So for this example, this particular result, what you have is, if I can find it here, so this is what you have, and then this was my setup and the boundary condition. So I have ports. Let me show it first. So I have a port, a second port at the other end, and then the boundary condition that I put was electric boundary condition, so your PEC, and the waveguide port boundary condition actually overwrites that. So that's kind of a summary. I think it was still a bit long, but that was the summary of it. And if you already got the point of it, you can stop the video here and go do some other things. But then yeah, I'll now go through the simulations themselves. So for the first case, I looked at the exciting one of the faces of the rectangular waveguide with a waveguide port mode, which was the T11 mode. If I can look at it, oh, no, the T11. Oh boy, where is it? Oh, now I can't see this. Port 1, yeah. So I excited it with this mode. It should be T11. You can see here T11 mode, and what you have is the boundary conditions. I have PEC at the other side. Close this and close this and close this. Okay. So I have PEC at the other side, so the other end of the waveguide. And what I have is, from this, the result I have is below the cutoff frequency of the waveguide, you have no transmission, of course, of the waves through the cavity, but then above the cutoff frequency, which is around 750 megahertz, now you see the correct scale, around 750 megahertz, you have that all the T11 mode energy that is transmitted to the other part of the other end of the waveguide is reflected back. So that's why you have this value. So you have 0 dB, and that is maximum reflection. That's what you notice here. So all the waves are reflected back. You also notice the same thing for the PEC. But then I don't know if someone can explain this resonance. I didn't think too much of it, but now I'm thinking about it. If you can explain this resonance that you see, this notch that you see for the PMC boundary condition, maybe leave it in the comment. But then aside that, this is below the cutoff frequency, above the cutoff frequency, you notice exactly the same thing, which means your PMC also reflects the waves, the wave energy back from the other side. Now for the open boundary condition, which is here, so open boundary at this point, and then your waveguide excitation at this point. What you have is, so my boundary condition, just to show you that it's indeed open boundary condition. What you have is this, and I was of the impression that for the open boundary condition you actually had no reflection. So this actually shows that you do have some reflection of the wave back to the back into the system basically. And what is implemented for the open boundary condition is a perfectly matched layer, and I'll show it here, and it has some parameters that you could play around with. I think I played around with just this, so the estimated reflection level. Now I do not have the formula, but then you could look it up and see the formula for the perfectly matched layer boundary condition. So that's what you see, a PML boundary condition, and you could play around with this. But then I played around with this, and at least visually there was really no difference between the reflection, between the transmission properties. Maybe for a different video, I would really make it concrete and vary and do a parameter sweep and vary this. What I did notice was when you change the fraction of the wavelength, you actually had a difference. And I didn't, that wasn't the point of the study. I didn't really look at it that much. So maybe in a future video, I would do that. But then all of these parameters, I think they should affect how your open boundary condition reflects. But then I don't think you ever get a perfect transmission, so that's with zero reflection for the PML boundary condition, that's the open boundary condition. So for the conducting wall, I used copper, so a conductivity. So if you should check this, one of them is conducting wall, and there is a conductivity of 5.96 e⁻⁷, and that's the conductivity of copper, at least standard conductivity I saw online. That is also default in CST Studio. Oh, I didn't even speak about the modeling. The modeling is of the rectangular waveguide is not difficult. It's just click on brick and then escape. Then you put your dimensions, which I have here. It's 500 millimeters long, 100 millimeters high, and then 200 millimeters wide. I think I mixed up the representation. A is supposed to be equal to 2b, but yeah, that's just some slight stuff. So for the conducting wall, you also had the same transmission parameters as your perfect electric conductor. I'll show all of them together. Then for your open boundary condition with space, this was just trivial because this also behaved like a conducting wall. And maybe pause for a second and think about why this is the case. So I'll show the boundary condition. So open boundary condition with adding space, which means you do not put the open boundary condition exactly on the face of your model, but you give some space before you do it. But this behaves exactly like it doesn't behave like an open boundary condition, it behaves exactly like the perfect electric conductor and the conductor. So maybe you could pause the video and think about why this is. Yeah, now I'll say it. The reason is because it doesn't actually capture the intention. I would guess that someone that puts an open boundary condition with space would imagine that probably this should be vacuum or something like that. I mean, I'm just imagining that this would be some vacuum or something. But then notice that in our background material, this is spec. So any space we're adding is being filled up with the perfect electric conductor. So this case is really trivial because it's like we're just putting a perfect electric conductor brick to this point and then trying to get the then you have that this surface here is still exactly the same as the PEC. So in order to study this effect, one would have to, let me show that again, background. You'd have to construct your model differently, which is instead of constructing the vacuum space, you would have to construct the surrounding space of the waveguide, and then you can apply this boundary condition, and then you change your background properties to normal, which means that this space would now be filled with vacuum. So yeah, just pointing that out, but then it was a trivia case, that's why I didn't show it in the final result. Then for the waveguide port boundary condition, now remember, starting this, I wanted to see if this overrides every other boundary condition, and I checked for the electric. Did I check? I think I also checked for the magnetic, and he overrode that, but I didn't check for the rest because I suspected anyhow that it overrides it. So you see that Z mean the boundary condition here is electric, right? And also Z max is electric, but you do not have the same behavior as when you put only PEC, and that's because your waveguide port boundary condition overrides it. Even if you should put an open boundary condition here, you would have exactly the same properties that I'll show you now, which is your waveguide port boundary condition overrides it, and this is what we have for the transmission. This is, I mean, compared to the rest, this is really good because you have minus 45 dB even. So this is your resonance, which is around 700, not resonance, cutoff frequency, which is around 750 megahertz, and you have that even for modes that are for frequencies that are close to the cutoff frequency. You have really good transmission property. So this, what we're looking at is the reflection, which is minus 45 dB, so that's really low. And then you have that it's yeah, it's increasing gradually, but I think I check up to 10 gigahertz. Now I don't know where I kept the result, but I checked up to 10 gigahertz, and you had that even though it's increasing, it still was below, I think 40 minus 40 dB, if I remember correctly. You can also check. So far I've been, or for the simulations I've shown, I looked at just one mode, and I wanted to see if this was the same, this behavior was the same for different other modes. So I did exactly the same study with a waveguide port boundary condition for 3 modes, and these were the results. So what I'm looking at is S11, and for the 3 modes, so yes, one parameters for the 3 modes, and you see that they are all below minus 40 dB, even up to 4 gigahertz. So yeah, that was the study. This was interesting to see. On the other hand, if we look at the transmission properties, then you see that at port 2, so if I look at S21, then you have that so this is S21 mode 2 mode 1, no, for the same mode. This just means that the, okay, I won't explain it, but just know that what we are looking at is S2122, yes, and then S2133. Yeah, so what you have is you have yeah, basically perfect transmission of the modes at port 2 if you should look at the transmission of the modes. So yeah, that was it. In conclusion, your waveguide boundary condition overrides the any other boundary condition you put, and then secondly, if you really want perfect absorption of your modes, then use a waveguide port boundary condition in your simulation and not your open boundary condition, because you still have some reflections, except um, maybe you're looking at really high frequencies, but then you still have to check, because I can't remember now if I did this up to 10 gigahertz to see if this got below minus 40 dB. So if you're using open boundary conditions and you do not want any reflection, then you should, I mean, it should be for cases where the frequency you're studying is not close to the cutoff frequency of your port or whatever case you're studying. And here I showed the results, I think together. Where is it? Yes. In dB. So here I show the results together, where I'll just show open boundary condition, PEC, PMC, and waveguide port. So this is a comparison of the reflections that you have for all of them. So this was it. If you have questions, maybe leave it in the comment section. I think I already got some comments and questions, but then I've not really been active on YouTube for a while. Apologies. I would try to find time to get around those questions, or maybe you already answered it, but I'll still answer. Anyway, if you have any comment, also leave it in the comment section, or maybe there are some corrections of maybe some things I said that were wrong, or some other insights, or if you can explain the notch for the PMC boundary condition, then just leave it in the comment section, and yeah, see you some other time. Ciao.